does anyone want to try and explain the difference between non-increasing and decreasing, or non-decreasing versus increasing?
So they can stay equal?
Yeah, that's the whole point. They can stay equal. Right, if you say something is decreasing, that means that they can't ever be the same value, because the next one always has to be less than the previous one. But notice with the change in terminology here, when I say non-decreasing, I don't mean forever and strictly increasing. It generally does, but as Christian pointed out, it allows for this plateauing kind of effect. Likewise, the same in the other direction. So you see, you can't call it strictly increasing, because while it does have an uptrend, every now and then it kind of plateaus out, and that's not increasing. Likewise, with non-increasing, you could have a very similar kind of dynamic play out. If a sequence is either non-increasing or non-decreasing, one or the other, we call it monotonic. That's what monotonic means. So here's the big theorem for this section. If you can show that a sequence is bounded and monotonic, then you're guaranteed it converges. To your point, Christian, like in the last one, this doesn't necessarily work in the other direction. Because you take this cosine n over 2 to the n, you see this will actually have oscillating terms because of the cosine. Like that. The limit does exist, right? But you see it's not monotonic. So you can't turn that around. But in the event that you can identify those two qualities of a sequence that is bounded and monotonic, you're guaranteed that it converges. Right? And then we don't go through the proof in here. That's an analysis kind of topic. But does that kind of make sense? That if there's a ceiling and a floor, I mean, that's really what we're saying, right? You've got the sequence. You're guaranteed that there's a ceiling and a floor, and it's either non-increasing or non-decreasing, which means it never turns back around. Right? So in other words, it's always going to be in some way heading up towards the ceiling or heading down towards the floor, then you're guaranteed convergence. That's the idea behind the bounded monotonic sequence theory.
It can converge to something other than 0.
Oh yeah, it can converge to something other than 0, absolutely. Now, this doesn't help us ever determine what it converges to. So realize that. This will justify whether it converges or not under certain circumstances, but it doesn't help you calculate the number.
So then why is it useful to know that?
Well, you're actually going to encounter an entire chapter worth of series here where you can use Mathematica to figure out what number it converges to, but there's no way to use a formula to figure out how it converges. This will make a little more sense probably early next week when we get into series more, the end of today. But there's a lot of forms where to actually calculate, you actually have to look at the individual terms and start punching a calculator and getting, adding it up. There is no formula that allows you to do that. So sometimes it is useful, and it happens a lot in mathematics. A lot of times in mathematics, we can prove something exists even though we can't find it. It's a very, very common thing to encounter in mathematics. Yeah. In fact, a lot of my research, I end up, during the first few weeks, what I do is I prove an existence theorem for whatever I'm looking for, and then I spend many, 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 many months after that actually